Good evening. We all know of the fortitude of astronomers arising in the evening to spend all night at their telescopes. Now we see that astronomy audiences are equally resolute coming out in weather like tonight's. So thank you very much. Before tonight, Darth Vader might have been the only man you knew of to cause the loss of an entire planet. Tonight we are privileged to welcome another such individual, Professor Michael Brown of Caltech, who with Chad Trujillo at Gemini Observatory and David Rabinowitz at Yale is responsible for the fact that our solar system today has only 8 planets rather than 9. This distressing news resulted from the team's discovery in 2005 of a new planetoid, Eris, that is larger than Pluto. In 2006, the International Astronomical Union categorized both Eris and Pluto as dwarf planets, just 2 of several large objects that don't fall into the Planetary Club. Welcome to the January Capital Science Lecture. I'm Bruce Ferguson, a member of Carnegie's Board of Trustees. I'm standing in for Carnegie's president, Dick Meserve, who's on travel at Carnegie's Astronomical Observatory in Chile. Dr. Meserve asked me to extend to our guest and to our speaker tonight his regrets that he couldn't be with us this evening. However, I'm particularly pleased to be substituting for him, given my long-standing interest in space science. A company I co-founded many years ago has launched several space science missions for NASA, one as far as Mars. To our speaker, though, Mars actually doesn't seem all that far away. Dr. Brown studies the distant realm where Pluto resides, called the Kuiper belt, between 3 billion and 5 billion miles from the Sun, or about 50 to 90 times the distance from Earth to our next-door neighbor Mars. Because of the difficulty in traversing such vast distances, it was only 2 years ago that NASA launched its first mission to Pluto called New Horizons. But the Kuiper belt is so far away that only in 2015, 9 years after launch, will New Horizons arrive at its final destination. Carnegie itself has a distinguished and rapidly evolving role in planetary science. To list just a few current initiatives, Sean Solomon is principal investigator on the Messenger mission to Mercury, which yesterday began providing us with exciting new images of the planet following a successful flyby. Congratulations to Sean. Alan Boss is pioneering new methods of modeling the formation of planets. Paul Butler has identified dozens of giant planets around other stars, and Alicia Weinberger is now learning what some of these planets have in their atmospheres. With so much work on distant frontiers, we hardly expect to hear of the discovery of objects within our own solar system. But in 1992, Pluto's domain in the Kuiper belt was recognized as new territory for prospecting. Today it is thought to contain tens of thousands of undiscovered icy bodies with diameters greater than 100 kilometers. To many astronomers, including our guest tonight, the Kuiper belt is the new frontier of planetary science. It is a dark, frozen realm, the deep ocean of planetary research, where observation is difficult, but the opportunity for discovery is immense. And Dr. Brown's team has indeed discovered many interesting objects. In addition to Eris, they have identified at least 2 objects about 3/4 the diameter of Pluto. Dr. Brown's scientific skills are accompanied by a sense of humor. Until the International Astronomical Union put its foot down, the dwarf planet Eris was provisionally named Xena after the character played by Lucy Lawless in the acclaimed television series Xena Warrior Princess. Michael Brown is professor of planetary astronomy at the California Institute of Technology. He received his undergraduate degree in physics at Princeton and his MS and PhD degrees at the University of California, Berkeley. He joined Caltech as an assistant professor in 1997 after serving as a Hubble postdoctoral fellow both at Caltech and at the University of Arizona. In 2003, he became a full professor at Caltech. His awards include the Presidential Early Career Award in 2000, the 2001 Urey Prize of the Division for Planetary Sciences of the American Astronomical Society, and Caltech's 2007 Richard P. Feynman Teaching Award. In 2006, in a rare recognition for an astronomer, he was named one of Time magazine's 100 most influential people on this planet. The woman who, as an 11-year-old girl, suggested the name Pluto is still alive today and has in turn had a planetary body named after her, the asteroid 6235 Bernie. So within a single lifetime, Pluto has gone from undiscovered planet to ninth planet to dwarf planet. To my knowledge, Professor Brown has not yet had a planetary body named after him. We can be confident, however, that in keeping with this scientist's remarkable career of exploration and discovery, when an astronomical object is one day given his name, it will prove to be a very interesting object indeed. Professor Brown.
So I have to correct some of this, which I do have a planetary body named after me. It's an asteroid. It's called Mike Brown, all one word, and it's not very bright, and it's quite eccentric. Not sure what that means. So and you missed my favorite of my honors that I got back in 2006, which was also Wired magazine online. Top 10 sexiest geeks, which my wife finds sort of appalling and sort of amusing all at the same time. So tonight I'm going to talk about Pluto and Eris and these other dwarf planets in the outer solar system. But the real title of my talk was a little bit stolen in the introduction, which he didn't even know the real title of my talk, but it's really How I Killed Pluto and why it had it coming. Because yes, in fact, I did sort of kill Pluto, and more importantly, it really did have it coming. So I'm going to tell you why, and also I'm from Caltech, which is right there, and it's a lot warmer there than it is here. So the story of how I killed Pluto and why it had it coming really starts with the discovery of Pluto, or really starts earlier than that with the first attempts at the discovery of Pluto, and there had been speculation about a planet outside of Neptune for a long time before the discovery of Pluto. People had thought that Neptune looked like it was being tugged along its orbit by something exterior, and they thought they could use that to calculate where something was. We now know that, in fact, that's not true. It's not being tugged along. Those were just some data that were a little flaky. But it didn't stop people from trying, and one of the people who tried went to Mount Wilson, this mountain that's right above my house in Pasadena. There's a nice big telescope up there. But before there were even telescopes up there, there were some, well, there's some big telescopes. There's some small telescopes up there. He went up to the mountaintop, took some pictures of where he thought this planet was going to be, Planet X he called it, and the picture looked sort of like this, and there it is. Somewhere. Well, that's kind of what he said. He was looking for a new planet, and he took a picture, and he thought that the planet was going to be there, and took a picture like this, and sure enough, if a big planet had been here in this field, it would be sort of this size. You know, Saturn would look like this with big rings around like this, and there's sure enough, there's nothing like that. But purely coincidentally, this picture that he had taken actually had Pluto almost dead center of it. This was long before the discovery of Pluto, but he didn't realize that Pluto was there because he didn't do the one step that it took decades longer to take, which was to realize that if you're really looking for something out in the outer solar system, you're looking for planets out there, and you don't know what they look like or how big they are, you have to do one thing. You have to take a picture one night, and then you have to come back the next night, take another picture, and see it move. You guys saw that, right? All right, let's try again. Here's first night. These are actually the discovery images of Pluto taken by Clyde Tombaugh in 1930. Here's the first night. Watch carefully. Second night. Who saw it? Who saw it? Liars. Here's the first night. Here's the second night. Anybody saw it? Who thinks they saw it? Yeah, okay, we'll see. So I've learned this thing. It's sort of this physiological thing. If you repeat something 3 times, when you do it the 4th time, everybody suddenly sees the pattern. I don't know why it works, but it seems to work. So here's the 4th time. There it is. There it is. Okay, how many of you? Okay, everybody has to be honest. Who raised their hand and said they saw it, had it right? Okay, a couple of you had it. Okay, there it is. And this is it without the arrows. There it is. There it is. That's Pluto. There, it's that one, right? Is that it? Okay. I always lose it in there. So you can see why it wasn't found the first time, because it's really quite small looking. It's not. These are just stars. All these stars are much brighter. This little thing looks like any of the other little stars out there. Just this tiny little thing that is indistinguishable, except by the fact that it moves. Now, when it was found back in 1930, people were a little surprised because they thought they were looking for this thing that's this big out there, and this tiny little thing out there was just didn't make sense. So people had all kinds of good theories for why it looked so small. They were less constrained back then to sort of deal with science like we are now, or maybe reality like we are now. So they came up with some really crazy ideas on why it looks so small. My favorite of the crazy ideas goes something like this, is that it's actually really it looks small, but it's actually really big. But what it is a uranium core, just like we have an iron core, this one is uranium. Uranium core covered by liquid oxygen oceans. Now, why? Just because it works. If you had a uranium core covered by liquid oxygen oceans, that liquid oxygen ocean would act like a big lens, and it would even make the uranium core look smaller. And uranium is really dense and heavy, so it would still be a big planet. So that's why it looks so small, because it's that little core, and it's actually really this big. So these days, we actually have progressed a little further than uranium cores and liquid oxygen oceans, and we know why it looks so small. Any guesses? Because it is. Yeah, this was an astounding bit of scientific deduction. It looks small because it's small. Pluto is actually, it's about half the size of the moon, and the moon is about half again the size of the next largest, the smallest thing that we now call planet Mercury. This thing is really small compared to any of the other things that are planets in the solar system. Which itself was strange, but what the other strange thing about Pluto when it was discovered was that it had a very odd orbit around the sun. If these are the giant planets, Jupiter, Saturn, Uranus, Neptune, all the little planets are inside here, they're all very nice. They go in nice circular orbits around the sun. If I tilted the screen sideways, you would see that they're all in one disk around the sun. If you throw Pluto into that mix, Pluto does some weird things. It dips inside the orbit of Neptune right here. It's very elongated, not circular at all. And if again, you turn that screen sideways, you see it's tilted by about 20 degrees compared to the other planets. Very strange. It just didn't quite fit in with the planets at the time. It looked small. It had a funny orbit. But at the time in 1930 when it was discovered, there was really nothing else to call it. Nobody knew about any of the other things out here. People knew about asteroids inside the orbit of Jupiter, but it didn't make any sense to call it that. So it was called a planet, and it stayed there in good standing for many, many years. I want to show you another view of the solar system, though, that really drives home how strange this thing is. Here are, and I'm going to show you this over and over and add things. So I wanted to walk you through it here. Here are all the planets that we know. There's Mercury that we just saw new pictures of. Mercury, Venus, Earth, Mars. Big Jupiter, Saturn without the rings, Uranus and Neptune, and you can really see that that there are big differences between these planets. You can also see, again, here's Mars and here's Jupiter. Between Mars and Jupiter, you see these little dots. These little dots are the asteroids, and I've actually drawn these asteroids as at their true sizes. The biggest one is right there, is the asteroid Ceres, discovered in 1801, and there are about a dozen asteroids that are large enough. My criteria for including them was that anything that was large enough to appear as 1 pixel in PowerPoint got on the slide. So that's how many. There are many millions of asteroids that are even smaller, but that's how many of them are big enough for a PowerPoint pixel in through there. Okay, I'm going to add Pluto, that alleged 9th planet, onto the list, and there it is. You know, it doesn't fit the pattern. Whatever the pattern is, you can come up with a lot of different patterns, small ones, big ones getting smaller, something. That thing is not what you would want to see out there to fit the pattern of planets. So it's not surprising that it's had sort of a rough going of planethood for the last couple of years. Now, to find Pluto, Clyde Tombaugh searched a huge swath of sky back between about 1930 and about 1950. And the swath of sky that he searched was, if this is a map of the sky, and imagine this as like a globe, a map of the globe only looking outward instead of looking in. So here's where the North Pole is, would be the North Star up here. Southern Cross would be down here. Equator along here. This line labeled the ecliptic is that line where all of the planets would be found right along here. The moon goes along here, the sun. Clyde Tombaugh looked all the way from down here, all the way to up here, a huge swath of the sky, and found only Pluto. After he found Pluto, he actually thought there might be other things out there because Pluto seemed so small. But he never found anything else other than Pluto going on out through there. So he searched across this whole big swath of sky. I'm going to fast forward now to 1992. In 1992, the first new object outside the orbit of Neptune was discovered by some astronomers at the University of Hawaii out in this region beyond Neptune. And since that time, since 1992, in the 16 years since then, something like 1,200 objects have now been found in this region of space. This region of space is this region called the Kuiper belt. Here's, again, Jupiter, Saturn, Uranus, Neptune. Each one of these little diamonds is one of these objects in the Kuiper belt that some astronomer somewhere found the exact same way that Clyde Tombaugh found Pluto. Take a picture of the sky, come back again a day later, an hour later, some amount of time later, take another picture of the sky, and look for something that moves. Every one of these was something that moved in the sky that caught the eye of some astronomer somewhere. And you can see that these things are mostly in this region beyond Neptune, in this ring through here. Some of them have actually slipped inside the orbit of Neptune. These are ones that came a little bit too close to Neptune at one point in time and got a little bit of a slingshot effect. Just like when we send a spacecraft out to the outer solar system, we slingshot it past Jupiter to make it go faster and change its orbit. If one of these things get close to Neptune, it slingshots inside and works its way in here, and eventually becomes things like comets, things that we see in this region today. So this is also one of the places where comets come from. Pluto is that little blue dot right there. Even back 2 years ago, when we were perhaps crazy enough to still consider Pluto a planet, it was very clear that Pluto was part of this Kuiper belt, that it existed in through here. In fact, if you look at the orbit of Pluto does a really good job of sort of defining the inner edge and the outer edge of exactly where the Kuiper belt is. Pluto is, whether you agree it's a planet or not, it is part of this Kuiper belt. But for the first 15 years or 14 years of our knowledge of the Kuiper belt, you could still argue that Pluto was a special member of the Kuiper belt. If you put some of the largest known Kuiper belt objects on the plot over here, there's Pluto again, and here are, by about 2002, here are all the known Kuiper belt objects that are, again, big enough to be a PowerPoint pixel. Most of them are single dots. Some of them are getting a little bit bigger. The biggest ones are maybe a quarter or a third the size of Pluto, starting to get a little bit bigger. But if you were desperate to want to consider Pluto special and still be called a planet, your last recourse was to say, hey, well, okay, sure, it belongs to these guys, but it's a lot bigger, and by a lot I mean 3 times. But it's a lot bigger than all the rest of them, so we're going to call it a planet. It's still a planet, no matter what anybody says. Well, this is about the situation that we were in around about 7 years ago, when we started thinking, I wonder if there are larger things that are actually out there that we should be looking for. Because an interesting thing had happened, which is that Clyde Tombaugh had looked through about this much sky, looking for Pluto. Those 1,000 Kuiper belt objects that I showed you on that plot there, the total amount of sky that astronomers had looked at to find those objects compared to Clyde Tombaugh is about that much. And I gave this talk to a third grade class recently, and one of the third graders raised his hand at one point. He says, "Okay, so why are astronomers so stupid?" And I'm sad to say that's the subject of another hour-long lecture. But this part, the astronomers are actually not stupid. It's not that they are so stupid as to think, wow, I'm just going to look here, I'm going to ignore these little spots here, and I'm going to ignore these spots here and ignore these spots here. It's that technology, while has been great for astronomy in so many ways, in one way, we have been a little bit hurt by technology, and we have not been able to do what Clyde Tombaugh did back in 1930. And here's the reason why. So what's better? Telescopes are better than they were back in 1930 when Clyde Tombaugh did it. Computers are better. We were able to do all the stuff computer-controlled instead of having to do it all by hand like Clyde Tombaugh did. We use digital cameras instead of doing things photographically. Much, much better, much easier. The one thing that's worse, though, is our ability to look at large swaths of the sky at once. Clyde Tombaugh, when he wanted to look at a large swath of the sky, he used photographic plates, literally a piece of glass. Take your piece of glass and paint photographic emulsion on the back of it, slap it on the back of the telescope, and look at a big swath of the sky. When he looked at a big swath of the sky with he looked at a bunch of sky that's about this big. That's a pretty big chunk of sky all at once that Clyde Tombaugh could see. If he wanted to change how much sky he wanted to look at a little less sky, he could cut a smaller piece of glass, a little more. He could, within the limits of his telescope, cut a little more. So he could very easily adjust it. These days, it's not so easy. We do digital cameras instead of photographic plates. Digital cameras are so much easier. We don't have to put them on the telescope, take them off, develop them in the dark, breathe all those fumes, all these things. But the one thing that's harder is we can't make them arbitrarily big. There's only one way to make them bigger, and you know the answer. What if you have a digital camera and you want to have more megapixels in your digital camera? How do you do that? Spend more money. That's the answer. And sadly, even the spend more money has its own limits. The biggest digital cameras these days, I like to ask this question because it's always interesting to see how it goes. If you're someone like me who buys a new camera every year, well, I only buy a new camera every year because I lose mine every year. But if you lose your camera and you buy a new one every year, what happens every time you buy a new camera every year? Yeah, you pay the same amount of money, and you get more megapixels. Everything's better. So I always spend like $300 on a camera. And if you spend $300, how many megapixels do you get these days? 8? Jeez. Okay, I'm going to go lose my camera as soon as I get back home. I think I still have 3. That's probably like pathetic now, right? So it just keeps going up and going up. In fact, who here thinks they might have the largest number of megapixels on a handheld camera? None of you astronomers out there. On a handheld camera that they actually own. Who thinks they have? How many you got? 12? Anybody beat 12? 12. Oh. I gave this talk to a group that I didn't realize included some professional photographers, and one guy had some 50 megapixel large format digital camera, so I was blown away. But 12 is pretty good. 12 is a lot of megapixels. So you'll be a little impressed, but increasingly less so as time goes on when I tell you the camera that I use to take these pictures is a 180 megapixel camera. And it was built 7 years ago. That's the part that was impressive. At the time when it was 7 years ago when we built it, people had 1s and 2s, and so 170 seemed a lot. It is currently the biggest digital camera anywhere on a telescope until something like tomorrow when there's a bigger one. I mean, literally almost tomorrow when there's a bigger one. But we're using this to cover much bigger parts of the sky than anyone else had ever done before. And this is one of the reasons why we're able to start to find these new things that no one else had done. The other thing is that we have a telescope that's a fabulous telescope for these purposes. This is the Samuel Ocean Telescope at Palomar Observatory. Palomar is the big observatory outside of San Diego that for a long time had the biggest telescope in the world, the Palomar 200-inch telescope that was a joint venture at the time between Caltech and Carnegie was part of this. This is not the 200-inch telescope that was the biggest telescope in the world. This is the little 48-inch Schmidt telescope that was built at the same time, sort of as the finder telescope for the big telescope that sits sits over here. This one had sort of been fallen into basically disuse because it's small. Nobody wanted to use it. Plus, it had photographic plates, which nobody used. So we took it, we refurbished it, made it robotic, which is fabulous, and put in this big digital camera. And we added one more thing, which is the best thing in the entire world, which is this. Doesn't look like much, but it is a little microwave dish that points to a little tower in the woods over here, which eventually points to the San Diego Supercomputer Center, which eventually transmits up to my office in Pasadena, which means that the entire thing is run autonomously. I've used this telescope 20 nights out of the month for the past 7 years, and I have been there twice in 7 years. I mean, I think, and this is important. I'm willing to go spend large amounts of time at a telescope, but 7 years in a row, I'm not willing to do it. And even my graduate students, I can't convince to go spend 7 years in a row. So they're getting lazier these days, I think. But robots, you can convince to do these things. So, combination of big camera that can cover a lot of sky, a telescope that we get to use all the time, and thorough robotic, we have been able to do a fairly amazing thing. We've gone from astronomers having covered this much sky to we have, all by ourselves in the last 7 years, covered about this. Well, that's good reaction. Let's try it again. Everybody else, us. Whoa, yeah. So the cool thing about this, there's so many cool things about this. Let me tell you one cool thing about this, is that we have finally, it was about 2 years ago, finally surpassed Clyde Tombaugh in 1930. It took us all that time and all this time to get as much as he did. But the nice thing is, because we have digital cameras, because we have it robotic, we get to see a lot of the things that he didn't get to see. Let me walk you through this real quickly. This is this swath in through here, where we mostly didn't look at it over here and we tried over here, bad idea, is where the Milky Way galaxy crosses across the sky. And the Milky Way galaxy has so many stars in it, it's not worth looking there, basically. So we stopped. We tried it 1 year, gave up. We can't see south of here. This is the southern hemisphere. Without digging some really deep holes into the mountain of Palomar, we can't see into the southern hemisphere. So we hope to start there sometime in the near future. And this little patch right up in here, which comes over here, is we finally, after 7 years, gave up. It is the far north that's available to look at in January and February. And if you have been in Southern California in January or February for the past 7 years, you would understand that it has not been clear almost any night in January and February, so we really have given up that part of the sky. But otherwise, we covered big swaths, and I'm going to now walk you through what we do and some of the things that we see. That little red dot right there is, I hate to say it again, but it's the smallest dot you can make in PowerPoint. I'm going to show you a piece of sky that is 10 times smaller on each side than that dot. So a tiny, tiny, tiny piece of sky, and these are some of the pieces of sky that we look at night after night after night. Here's how it works. The robotic telescope takes a picture of the sky. It comes back an hour and a half later, takes another picture of the sky. Comes back an hour and a half later, takes one more picture of the sky. We have those 3 pictures. Those pictures come to the computer in Pasadena every morning. The computer does most of the hard work that Clyde Tombaugh did by hand of sorting through, looking for the things that are moving versus the things that are not moving. And it picks out a few little postage stamps, of which I'm going to show you, and it says, hey, I think this is real. I think this is real. I think this is real. I'm only going to show you the ones that are real. The computer only finds about one real one for every about 100 things that it points out. But looking through those by eye is not a very hard thing to do. And your eye and your brain are an incredible combination for really understanding what's real versus what's not real. They're much better than computers in the end. It's the whole problem with computers and visual recognition. There are so many things that can go wrong that your eye instantly recognizes, oh, that's just that it would take forever to program a computer. So the final swath is always done by eye. So let me show you some of these things. Here are a couple. Here's stars, star, 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 star. Oops, and there's something moving. There it is. Little thing moving in 3 images over the course of about 3 hours. These things, they look like they're moving by a lot. They're not actually moving by that much. They are moving by a total amount of, if you pluck a hair out of your head, and you have relatively thin hair like me, and you hold it at arm's length, these things move about that distance in a day. across the sky. So it's a very tiny motion, but with the big telescopes, you can see it quite readily. This object, the other important thing to know is that when we're looking for these things that move, we can tell how far away they are by how fast they move. Things that are close to us zip across the sky very quickly. Things that are far away move very slowly. Things that are really, really far away, like stars, don't move at all. So we can quickly sort how far away they are. We can also make a good guess at how big they are by how bright they are on the screen here, too. So I'm going to go through and sort of guess how big all these things are. Who wants to guess? So we're looking for these things that move pretty slowly. What do you think the fastest moving things we ever see are? Anybody guess? Yeah. Asteroids, satellites? Nope. Somebody over here got it. It's airplanes. Airplanes. We are in the landing pattern of the San Diego airport, and but airplanes are not only fast; they're also really big. They cover about this much of the screen at once, and so we have to start over again. But mostly, we see a lot of we see satellites. They move pretty quickly too. We see asteroids, those things between Mars and Jupiter. I'll show you some here in a minute. And finally, moving very slowly, we see these objects in the Kuiper belt. So here's one moving along. This one is moving at a moderately slow speed compared to some of these other ones we'll see, and it's moderately faint. So this one is about, so I'm going to compare everything to the distance of Pluto, which is about the distance of Neptune right now. This one's about just a little outside the orbit of Pluto, and it's pretty small. It's probably about 200 kilometers across. Pluto, in comparison, is about 2,300 kilometers across. So think of this as about 10 times smaller than Pluto, this guy right here. Pretty small and pretty typical. And we found something like 70 of these objects that are kind of like that. Here's another one. It's moving a little bit more slowly and more jumpy for some reason. And you can see, this one's interesting just because you can see some of all the weird things that happen when you take these pictures. Bright stars cause these big saturations. The same thing happens if you take your digital camera and take a picture of the sun or somewhere close to the sun. You'll see all these streaks like this. We get the same problems. Sometimes there are problems in the camera. Your eye looks at that and says, junk, junk, junk. The computer gets a little confused, but there's one. It's a little further away. It's more like half again the distance of Pluto, and it's similarly bright to this one, but because it's a little further away, we know that it must be a little bit bigger, so maybe 300 kilometers. No, north actually is in this direction on all these images. Yeah, actually, you know too much. Or it's in this direction. Let me think about this for a second. We're moving this way. They move this way. Nope, north is this way. So it's because what I didn't tell you, to get into I'll very quickly digress and tell you the details on this, which is that speed, I sort of made it sound like you're seeing the speed because these things are going around the sun. You can almost ignore the fact that these things are going around the sun. Really, the only thing you're seeing is parallax. That same thing that you see if you're driving in your car, you look out the window, the mailboxes that are right next to you go by really quickly. They're moving fast. The house that's half a mile away looks like it's moving slowly. The mountains in the distance don't move at all. And that's really all you're seeing. The fact that these things are moving is actually, I will admit, irrelevant. It's simply the distance away from you that you're seeing to the first order. So you get a good guess just from that. All right, here's some more that we'll see real quick. Typical speed, that was sort of like the last one. Here's another one moving very slowly, a little bit more slowly, a little bit brighter. This one's about 500 kilometers. Also, there's an asteroid. Let's see, 1, 2, is the third one? There's the third one right there. 1, 2, 3. See that asteroid? 1, 2, 3. That asteroid is moving maybe 10 times faster, so it's about 10 times closer. It really is just a simple proportion going on in there. And I'm going to just show you a few more. Here's a nice bright one moving kind of slowly. This one's pretty big. This one's probably about 800, 900 kilometers across, about a third the size of Pluto, at about a similar distance. This one's moving slowly, so it's out at that outer edge of the Kuiper belt, but it's kind of faint, so it's not that big. Lulling you to sleep here so that I can then astound you. One more of these here. Here's another one moving along here, not so interesting. Nice, bright, kind of far away, 800. Some of these things are, I sort of say dismissively a third the size of Pluto, which is, of course, bigger than most anything else that had ever been found before in this region here. So still big, but still, nothing that would make the news. unless it hit us, in which case there wouldn't be news, so it doesn't matter. Now, now that I have lulled you into sleep, I want to show you what happened to me. This was today, the 16th, 3 weeks and 11 days ago. 3 weeks, 3 years, weeks, years, whatever. 3 years and 11 days ago, I was sitting in my office and looking at data and flipping through all these things, and what do I see? But this one. And I literally almost fell out of my chair because I really slouch, and so you don't have to move very much to fall out of your chair. And so, okay, why did I almost fall out of my chair? What's so astounding about this one? It's big, which is not really, it's bright. You can't really see the size. It's bright, and it's slow. So slow is good. This thing is about half the speed of anything else that I had just shown you, which means anything else that we'd ever found, which means it's twice the distance of anything we'd ever found. I showed you some of those things were out at the edge of the Kuiper belt. This thing is twice the distance as the edge of the Kuiper belt. That's astounding. It's also bright. This thing was the brightest thing we had ever seen. Bright is good. Brightest thing we'd ever seen meant it was the biggest thing we'd ever seen. But couple that with the most distant thing we'd ever seen, and it was obvious. This thing was not just the biggest thing we'd ever seen. This thing was huge. And so I immediately picked up the phone and called my wife and said, I just found a planet. And she was 3 months pregnant at the time and said, that's nice. Please pick up milk on the way home. And I forgot to pick up the milk. But, okay, so why did I say I just found a planet? Well, I was pretty sure right then that this was something that was bigger than Pluto. I didn't know how big it was, though, exactly. I just knew that it was something bigger than Pluto. So now I've been sort of giving you sizes all along, but now I say I don't really know how big it is. And here's the reason why. This is one problem that has continuously faced us, is that we find these things, we see that they're bright, we see that they're far away, but we don't actually know how big they are when we first find them. And here's why. It looks big in this image because it's sort of smeared out, but it's really just so bright that it fills up a lot of the camera. It's just bright. All we see in that picture is a little point of light, and that's very far away, and we have no idea how big it is. When we see that point of light, what we're seeing is reflected sunlight. The sun is somewhere over there. The sun is over here, shines, reflects off the surface of this object, bounces back off, and we see that light bounce back off. Actually, it takes about 12 hours for the sunlight to get out there, another 12 hours to get back, so we see yesterday's sunlight when that happens. And it reflects a lot of light, so it must be pretty big to reflect a lot of light, but it also could be reflecting a lot of light, not just because it's big, but also if it had, say, snow on the surface or something else bright. So it could either be big with snow on the surface and reflect a lot of light, or it could be huge with dirt on the surface, and it would still reflect a lot of light, even though the individual dirt doesn't reflect a lot. It's big enough to reflect light. We can't tell the difference right here. We knew that even if it was reflected, if it had snow on the surface, it still was bigger than Pluto. So we knew right away it was bigger than Pluto, but we didn't know how big it was. And I went back and tracked down the email that I sent to the two other guys I work with, David Rubinowitz and Chad Trujillo. I sent email to them that morning after we just found it, and speculating about how big this thing might be. Because we really didn't know. Is it snow on the surface? Is it dirt on the surface? And this email had a whole list. Okay, if it has a really, really bright snowy surface, it's bigger than Pluto. Okay, check. And I think at the bottom of the list was if it has sort of a moderately dark or very dark, like the surface of the moon actually is quite dark. If it's like the moon, this thing would have been about the size of Mercury, some very big object out in the other solar system. So we were very excited. We knew we were onto something, and we really wanted to know how big it really, really was. So the first thing we wanted to know, though, because we do want to know how big it is, but we actually are as interested in what sort of object it is. The first thing we want to know is also what sort of orbit does it have going around the sun? Does it have an orbit like those planets that are all in circles? Does it have an orbit like Pluto or the other Kuiper belt objects that are really elongated? Usually, the only way to find out is to track the object for a couple of years in a row to get enough of a feel for where it's going to be able to predict its entire orbit. I don't have nearly the attention span for doing that sort of thing. So instead, we tried something a little easier in some ways, which was to go backwards in time and look where it was. Sounds a little hard, but it turned out to be really easy. This thing is not that faint compared to the things that astronomers look at. You could easily go backwards, find images that other astronomers had taken, and find it. The trick is, no astronomer had ever taken 2 pictures in a row and seen it move. So in everybody's picture, it just looks like a star. Except that you realize, you look at somebody's picture that they took here, and then you look at somebody else's picture that they took at the same spot, and you say, hey, it's there, but it's not here. That must be it. And then so you could jump back a year, 2 years, 3 years. We eventually got it back 50 years. So we have pictures of this back to 1950. And we know the orbit extremely well, and the orbit looks like this. Jupiter, Saturn, Uranus, Neptune, that incredibly crazy Pluto, and here's this one, even more elongated than Pluto. And interestingly, actually, the reason it's so far away is not because it's never closer, but because it's at its most distant spot in its orbit that it's ever in right now. Turns out it has a 580-year orbit around the sun. And when it's closer to the sun, it's much, much brighter. So if you can wait 290 years till when it's over here, it's going to be an incredible object to be able to study. It's going to be sort of the Pluto of the time that we'll be able to see. So in some ways, you could argue that we're very unlucky. We don't get to study it in detail for now, and I should be sad about it. But I'll admit that I'm a little. If it had been here, it actually would have been bright enough that Clyde Tombaugh would have found it in 1930, and what would have been fun about that? So I'm happy it's way out there. I'm sad that I'm not going to be around in 290 years to see it brighter, but I hope some of you are still around to see it. The other interesting thing, remember how I told you that Pluto was tilted like this? Take this thing, turn it on its side, and I'm going to do it for you. Yeah, that's right. This 45 degrees. This is so extreme that there's still actually no good explanation for this. Pluto, we understand now. We think this one, people have tried to come up with explanations in the intervening 2.5 years, but no one has really figured out what's going on. Everybody blames Neptune, but they don't quite know what Neptune did to cause this problem. But we don't really know. Okay, so now we know what kind of orbit it has. It has an orbit. It doesn't look like the orbits of these big planets. It looks more like the orbit of Pluto and actually what a lot of the other Kuiper Belt objects look like. So that was our first clue that maybe it was not, when you first see it, you hope it kind of has a circular orbit and it's going to be this Mercury-sized thing out there, that it really is inarguably the 10th planet. But it's looking like it's perhaps more of a Pluto sort of thing. And what we really wanted to do was figure out how big it was. Now, astronomers have come up with really clever ways of figuring out how big these things are that you can't see. They're too far away to see, but you still want to know how big they are. And they involve doing things like taking pictures with things like the Spitzer Space Telescope, which measures the heat coming off of the body, and then backtracking how far away it is and the temperature and blah, 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 blah. And we had this clever idea that we thought, we're going to try something that's never been tried before. We thought we were very clever for figuring it out, which is take a picture and see how big it looks. So, well, there's a problem with that. Of course, I told you can't actually do that because it's so far away that it's just a little point of light smeared out by the Earth's atmosphere. But if you can get rid of the Earth's atmosphere, you might be able to do it. Or if you can go up above the Earth's atmosphere, you might be able to do it. So we took a picture with the Hubble Space Telescope. I just have to always stop and look because this is my favorite picture of the Hubble Space Telescope. There's the space shuttle robotic arm just releasing it. And this is the shield. Usually the telescope looks out this direction, but its trapdoor is closed to keep contaminants out of the inside of the telescope, and you see reflect. Those are Earth's clouds reflected in there. Just a spectacular image. And this telescope, of course, being above the Earth's atmosphere, can take incredibly crisp images of very distant things. And if there was a shot of seeing how big it was, this was the way to do it. So we took a picture, and I'm going to show you this picture now. And this is, except for the very youngest amongst you out here, I suspect, okay, you guys might see a better one, but everybody else, this is going to be the best picture of this thing you'll ever see in your entire lives. Ready? Here it comes. Nope, that's not it. Okay. Yeah, that's it. So, okay, so you're a little disappointed. Imagine me. So I was sitting here waiting. The telescope, you You can look on the schedule. The telescope is taking the pictures. You look up in the sky. You know what's happening. You're sitting there waiting by your computer till the email comes that says you can now collect your pictures and look at them. And I download them, and I put the first one up. And so I had thought, so remember I said it might be as big as Mercury. If it were as big as Mercury, it would be something like this big, like the disk. You would see things on it. It would be very exciting. This thing was very small looking and not very interesting looking. And to really figure out how big it was, we had to carefully compare this picture to a picture of a star that's right about here. And we finally realized really the actual disk of the thing is only about actually that big. That is as small as we possibly thought it might be. It's actually relatively tiny compared to what it could have been. What does that mean? It means it's bright. It means that the surface is incredibly bright. One of the reasons it's so bright and easy for us to see, yes, it's bigger than Pluto. This showed that it was about 5% bigger than Pluto with an uncertainty of about 4.5% or so. But bigger than Pluto, maybe, and but incredibly bright. This thing reflects almost 90% of the sunlight that hits the surface. Freshly fallen snow, even clean snow, not like the stuff out here. Clean, freshly fallen snow reflects something like 80% of the sunlight that hits it. Let the snow get a little bit dirty and it's down to 60%. The Earth reflects 40-ish% of the sunlight, depending on where you're looking. 90%. The only thing I know of in the solar system that reflects more sunlight than that is Saturn's crazy moon Enceladus. Do you guys know about this one? These pictures coming back from the Cassini spacecraft that show this moon around Saturn that has geysers out the South Pole, and these geysers shoot out the South Pole. This part's true. Some stuff I make up. This part's true. Geysers shoot out the South Pole. The ice falls back on the surface and coats the surface in ice daily, and it's incredibly bright and incredibly reflective. And okay, so we know what's going on there. This thing is almost as bright as that. I don't think that there are geysers going along at the South Pole of this thing. So what's going on? Well, this is one of those cases where you do sort of the three-step process of an unexpected result in science, which is you get the result, you think, ugh, what did I do wrong this time? Go back and you do it again. Step two. You go say, what did I do wrong this time? You go back and do it again, get the same result, and then you think, oh, I knew that all along. So here's why maybe we should have known it all along, although I admit we didn't know it all along. This thing is so far away from the sun, it is so incredibly cold that almost anything that's out there is going to be frozen solid. What's out there? Well, one of the things that's out there is probably, much like Pluto, this thing probably has an atmosphere, a very thin atmosphere, but an atmosphere nonetheless, of nitrogen, just like the nitrogen in the Earth's atmosphere, only a lot less of it. When this guy is close to the sun, close means still further away than Pluto, but close to the sun, that atmosphere will boil off of the surface and go out into the above the surface, and you'll have an atmosphere. But when it gets far away from the sun, really cold, it'll freeze solid on the surface. When it freezes solids on the surface, it covers everything in this very pristine frost. So I think this thing has just a tiny layer of frost covering absolutely everything. Same thing would happen to the Earth. If you took the Earth with its nitrogen atmosphere and you moved it out to where this guy is, all of our air would freeze solid, and it'd be about 30 feet high of nitrogen ice that we'd be buried underneath. This one's not so bad. It's only about a 100th of an inch of nitrogen ice buried underneath. But I think that's enough to totally coat the surface and make it really bright. Okay, so the size, of course, I told you, was just a little bit bigger than Pluto. Let's put it on the list here. There's Pluto again. I filled in some of these other guys because we started finding those guys too. This is the one, I remind you, this is the one, of course, that changed everything. This is the one that killed Pluto. And so this is it. Here it is. Changes everything. Oh, wait, there it is. Okay, everything's the same. Everything's different. Same, different, same, different. Did you see it? It's the one over here. It's that little thing right there. Okay, so the first question you have to ask yourself is, okay, what? Clearly, in the grand scheme of understanding the solar system, the fact that there's two things this size instead of one thing this size really doesn't make that much difference. It doesn't change anything out there. So why does it change everything out there? Well, what it does is, contrary to what everybody thinks, that vote that the astronomers did a year and a half ago was not really a vote to demote Pluto. It was actually a vote to decide what to do with this guy. And Pluto is just collateral damage. Because once you find something bigger than Pluto, you're forced to answer the question. If you don't ever find anything bigger than Pluto, you can always sweep it under the rug. Say, yes, we know Pluto looks a little funny over there, but it's the biggest one, so it's a planet. Once you find something bigger, you have to say, okay, Pluto's the biggest one, it's a planet, so what's this one? And nobody's willing to answer this question for a full year after the discovery until finally, in this big meeting, they finally had the debate, the question, what is this thing really going to do? And as everybody knows, in the end, the decision was that these things are not planets, that these 8 big ones here are considered planets. These little guys are considered dwarf planets, and the dwarf planets here are just part of this population in through here. And of all the people in the world who should have been saddened by this result, I mean, really, it was me, right? They killed my planet. I could have been a guy who discovered planet. I could have been the only living guy who discovered a planet in our solar system, but I have to say, it's really the right choice. It pains me to say so, but it really is the right thing to have done. And let me tell you why. Funny thing about this whole planet debate and whether and what you'd classify planets are is if you go ask any astronomer, of which there are some in the room you could go ask, try this experiment, ask them what they think about Pluto and the planet, and the first thing they'll tell you is, it doesn't matter. None of this actually matters. And the next thing they'll do is talk to you for the next 3 hours about why their ideas are better than everybody else's idea. I'm not going to spend 3 hours telling you this, but I'll tell you why mine are better than everybody else's. The thing that I think was lost in this whole debate about planets was that no astronomers argue about the classification scheme. Let's ignore the word planet for a minute. The word planet off limits. Throw it away. If the word planet had never existed to begin with, this would all been a lot easier. Scientists work by classification. Let's come up with reasonable classification schemes for these objects. Hey, I see one. Big things, medium things, small outer things, small inner things. That is a really good classification system. In fact, to me, that is the classification system that explains better than anything else the architecture of the solar system. It explains the architecture of the solar system. It makes you ask the right questions for understanding the solar system. It is a very good classification scheme. Now, I care about the architecture. I care about the formation of the solar system. So to me, this is the most natural classification scheme, and that I want to take the word planet, which is the word that we all know and love, and I want to slap it on that classification scheme. Planets, not a planet, not a planet. Actually, what I really want to do, these are planets, but these aren't either. But I don't think that one's going to fly. I try it in my class that I teach at Caltech. I force them to consider the possibility that Mercury, Venus, Earth, and Mars are really just debris that hardly matters either. But even they don't buy it. Okay, so planets, not planets. But there are an infinite number of other classification schemes that you might use, each one of them good for something else. When this vote happened, I got a lot of email from the public. People said, hey, why not say planets are things with atmospheres and things without atmospheres are not planets? Ignore the word planet for a minute and say, why not classify things with atmospheres, without atmospheres? Great idea. If you're interested in atmospheres, that's a very important classification. Of course you would do that. Somebody said, why not classify things as things that have satellites, things that don't have satellites? Great idea. If you're interested in satellites, that is an important classification to you. And the final debate that happened amongst the astronomers was, why not classify things as things that are small enough to have sort of arbitrary shape versus things that are large enough to be round? Now, round is an important thing. When you're round, if you take enough rocks and throw them up in space, they will eventually crush themselves into a round shape. And that round shape matters because that means that there's enough crushing going on that there might be geology, interesting physics happening on the inside. That's a very important classification. Round versus not round matters a lot. And that was the sort of the counter proposal for the thing that would have eventually become a planet. Now, round versus not round, Pluto would have been a planet. My guy would have been a planet. Everything you see here would have been a planet. This guy would have been a planet. There'd be about 200 planets. But who cares, right? Round versus not round is a very good classification scheme, and it's an important one, and we should think about it and ask questions about it. And then the only question, and this is the part that actually doesn't matter scientifically, but I think actually matters a lot culturally, is where do we draw the line and call planets? Because in the end, people care about planets. People do not care as much about these classifications for different ways of studying them. They really want to know what's a planet and what's not. And to me, at this point, it is a purely aesthetic argument. It has nothing to do with science. The science is all in the classification. No reasonable astronomer is going to argue against any of these as good classification systems. And so then the argument about what the word planet gets applied to is purely aesthetic. And in my aesthetic sense, 8 big important things describing the real important objects in the solar system, the individuals, those should be planets. These guys, any one of these things, if you took it away from the solar system, you wouldn't notice. The planets wouldn't notice. Nobody else would notice. Take away any of these 8, and everybody notices. It makes a big difference in the solar system. To me, aesthetically, that's the right way to do it. To you, aesthetically, it might be a different way to do it. But as with most things aesthetic, you take a vote, and whoever has more votes wins. And so the astronomers voted. I mean, some people have said, "Oh, this is a bad sign. It shows that science is not done by voting." But that's not the science. The science is the classification. The application of the word, the semantic part, was done by voting. And I think it was done the right way. I think that choosing the big important things and explaining to the public that these are the things that matter, I think that's the right way to do it. If you remember nothing else from this lecture, I want you to remember 2 things. One is that I was one of the sexiest geeks of 2006. And, right, no, you can forget that. No, but the other one is that I want you to think of the solar system as composed of these 4 things: big things, small things, and then populations here and populations there. And if you understand that, you understand the solar system more than almost anybody. And that's an important thing. If you think about it as round things versus not round things, to me, you don't understand very much. Some things are round, some things are not round, but you got to understand this. So I'm very happy with the way that it worked out. I'll digress very quickly because that's what I do best, except for the quickly part. When I finally got when I finally got classified as a dwarf planet. Dwarf planets, by the way, are, of course, all those round things. That classification of round versus not round is dwarf planets versus not dwarf planets. Or as I like to say, a dwarf planet is something that looks like a planet but isn't. So when it finally got to be a dwarf planet, we got to name it, which was very exciting. We finally named our object that had many different names for a while. We finally got to name it. We named it Eris, E-R-I-S. Eris is the Greek goddess of discord and strife. And we were very happy that no one had taken that name in the past, so we got to name it that. We got to do a little bit of science, too. I want to do a little science other than just the soapboxing here. As soon as we find these things, we go and go to every telescope we can get our grubby little fingers on to study it. And one of my favorites are the Keck telescopes on the summit of Mauna Kea. There's Maui in the distance here. And with the Keck telescopes and with this very fancy new system on the Keck telescopes, we were able to freeze the blurring of the Earth's atmosphere and take a picture of Eris. And we're pleased and astounded that it actually has a little blip next to it. And that's the moon of Eris. Somebody said, well, having a moon, doesn't that make it more likely to be considered a planet? And the answer is no. Mercury and Venus don't have moons. They're still planets for now. A lot of the objects in the outer solar system actually have moons. So having a moon doesn't help you planet, not planet, but what does help you do is having a moon helps you scientifically tremendously. Having a moon means you can weigh the object. As the moon goes around, the speed that it goes around is determined by how heavy the thing is on the inside. If it's a really heavy object on the inside, made out of uranium with an oxygen ocean, the moon will go around really quickly. If it's light, styrofoam, it'll go around really slowly. And so finally, this is such a bad picture because this has only happened very recently, we finally got enough data to see it all the way around. And the answer is, so I'm happy to say, actually, the answer is, I told you that it was 5% bigger than Pluto with a moderate uncertainty, but it is 27% more massive than Pluto with an uncertainty of only about 2%. So it's comfortably more massive, would have been quite embarrassing had it not been. But I'm happy to say it's really quite it is by a good margin the largest thing that we know of out there. We of course get to name the satellite too. The satellite is named Dysnomia, which is the daughter of Eris and the demon spirit of lawlessness. So before I end, I just want to show you a couple of the other objects we found. Everybody hears about Eris because it's the biggest one and it's bigger than Pluto and it causes all the problems. But there are a lot of other things we found that have been scientifically incredibly interesting, and I just want to give you a small flavor of some of the richness of the science that we're getting to do since we found these things. And just for scale, here's Pluto, here's Eris, just a little bit bigger than Pluto. And I want to show you some of these other guys that we found. The first one of these is just a little smaller than Pluto. These things don't have real names yet. It currently has the license plate number 2005 FY9. We found it the day after Easter, so we call it Easter Bunny. And we're currently trying to name it after one of the native gods from Easter Island, just because we think it's funny. But currently it's just called Easter Bunny. We'll call it Easter Bunny. The interesting thing about Easter Bunny is that, well, the funny thing about Easter Bunny, it is almost as big as Pluto. I mean, it's in the grand scheme of things, these things are triplets. They're about the same size. But of course, nobody's heard of Easter Bunny because it wasn't bigger than Pluto, and it was never even vaguely under consideration for being a planet for that first year after discovery. So it sort of shows you the sort of silliness of all this in some ways. The nice thing about it is that these three all are all very similar. They have those nitrogen atmospheres. They have frozen methane, natural gas on the surface of them. For a long time, Pluto was this oddball out there that was the only thing like it, and the only way to study this oddball was to just guess what other things might be like. Now we have these three that are the same, one's a little bigger, one's a little smaller, they're different distances. By studying these three different things that are similar but different, we can finally start to understand these things as little worlds and how these little worlds work. So I'm very excited to have found these and start to be able to study these. My favorite one, though, is this guy. I show it here as a really white, rapidly spinning oblong thing because it's a really white, rapidly spinning oblong thing. It is. It looks like this, and it's actually, this is the right size. It is on the long axis here, when you see it come by, is as big as Pluto. Actually, for a while, as these debates went all over the map, one of the ideas was that anything Pluto-sized or larger was going to be considered a planet. And I was going to then argue for this one and say it's a planet if you look at it now. Luckily, I didn't have to make that argument because it never got that far. But this one is scientifically, this one is, I think, my favorite thing in the world. It is 2003 EL61. We discovered it on December 28th, so we call it Santa. It's rotating so fast because it got smashed early on in the history of the solar system. It got smashed by another thing obliquely and started spinning. Because it's spinning so fast, it elongates out like pizza dough would. And as it got smashed, chunks of it went flying away. Two of those chunks are actually in orbit around this guy. So it has two moons around it that are chunks that got smashed off. And many of the other chunks we have now found floating in space in similar orbits to this out in the Kuiper belt, chunks of this thing that happened 4.5 billion years ago. It's a fascinating story, and we're learning more and more. I'm going to finally leave you, I promise this time, with one more object, probably my favorite object of them all, although I just said that about this one too. So they're all my favorites. They're like your children. And this was one that we found back in 2002. At the time in 2002, these were all the known Kuiper belt objects, not quite as many as you saw now. And we discovered this object that was here. This object was called Sedna. Some of you have probably heard of it back in spring 2003. Sedna at the time was the most distant object anyone had ever seen in orbit around the sun, very far there. And just like now with Eris, we wanted to know, is it in a circular orbit like this, or does it come back in like it would be if it had come from the Kuiper belt? And the answer is no. It does this. This was totally out of left field. We had no idea that anything would do this. This thing takes 11,000 years to go around the sun, and it's as close almost as it ever comes to the sun right now, right here. If it had been 100 years earlier or 100 years from now, we would have had no chance of seeing it because it would have been too far away and too faint. So we got incredibly lucky. We just can see it in this tiny little region right here. Well, we either got incredibly lucky, or the right way to think about it. Astronomers don't like to think of themselves as lucky for the most part. they like to think, okay, there's 200 years out of 12,000 years when we could have seen it. We could have seen it 1 out of 60 chance of seeing it anywhere in its orbit. And the easiest solution to that being lucky is to say there's 60 of them. And the other 60 are out in here somewhere. And okay, so maybe there aren't 60, maybe there are 30 and we got a little bit lucky, or maybe there are 100 and we got a little bit unlucky. There are going to be many more of these objects like Sedna out in this region here. The interesting thing about Sedna is about 3/4 the size of Pluto. If Sedna is 3/4 the size of Pluto, and if there are 60 of them, it's very easy to think about that there must be larger things out there too. If there's 60 of them that are 3/4 the size of Pluto, there may be 20 of them that are twice the size of Pluto, and maybe there are 5 of them that are 3 times the size of Pluto, and maybe there's 1 of them that's 4 or 5 times the size of Pluto in this region out here that we have just barely begun to explore. 4 or 5 times the size of Pluto, 1 of them out there that's 4 or 5 times Pluto is something like the size of Mars. I think it is not unlikely that in this region, this is Eris now looking in, but in this new region, much further away, looking out from in and seeing with the sun much further out in this region that we've just barely begun to explore, I think it is actually likely that we're going to find things that are the size of Mars, the size of Mercury. Maybe we won't find them quite so big, but maybe we will. I think this is the next realm of where we're looking in the solar system. And I'll just leave you with one last thought. I pay close attention to the news. This may actually happen in the next months to years. We may find these things. I will tell you, I don't have any right now in my back pocket, so I'm not giving you any inside story here. But we're looking, and we may just find them. And if we do find one, if you find something the size of Mars out there in the outer part of the solar system, the arguments are going to start over again. What is it? Is it a planet? It's bigger than, say, Mercury, but is it a dwarf planet? By the official IAU definition, it would be called a dwarf planet, bigger than some of the planets. Shockingly, I have to say, classification-wise, it belongs in the non-planet classification, and I would argue, even if it's the size of Mercury or Mars, that it's not a planet. But I would not be unhappy if we found it, that somebody eventually considered it the new 9th planet or 10th planet or 57th planet or whatever it is out there. So stay tuned, and thanks for braving the cold, and I'll be happy to take a few questions here. And I guess there are microphones, so if you go to the microphones, the people who are listening out in cyberspace can hear you. Hi, cyberspace people.
I'm a little disappointed you named the other 2 satellites for Pluto. You had Charon and then Nix and Hydra, and I'm kind of disappointed you didn't include his wife and pet dog, Proserpina and Cerberus. But I was thinking also along the same line, we demoted Mercury, Venus, the Moon, Mars, Jupiter, and Saturn from being stars.
The history of the word planet is fascinating to go read through. Originally there were 7 planets, and each one of them had a day of the week. Every one of our days of the week is a planet, including the sun and the moon. And when we finally realized that we were one of them too, that sort of got broken. But the word planet has had a long cultural history, and so any arguments that anybody gives you that this is historically wrong or there should be classical planets, if you're going to go with classical planets, I'm going to say it's Mercury, Venus, Mars, Jupiter, Saturn, Sun, and Moon, and that's all we stick with. But yeah, so but I as a scientist, if we're going to have to stick with the scientific definition, I like this 8 one. The solar system is well described by that one definition. Yes. Oh, over here. Sorry.
You mentioned that the half period of Eris was about 290 years. Is there any record in 1710 of a bright spot in the sky?
No, that would be great. 1710 is too early. There were no telescopes at that time capable of having seen something as faint as that. When I said bright, I mean bright for astronomers, not bright for normal humans. So no, nothing like that. And likewise. Nobody saw Sedna 11,000 years ago during the last ice age. Yeah.
2 quick questions. One, in your photographs, there was an apparent wave pattern in several of those. Is that significant? Second question, is Pluto Has anybody looked at the possibility of Pluto might impact Neptune at some point in the future?
So both of those, the first one, is it significant? No, it's a long technical story about why it's there, but no, it's not interesting. It's actually in the camera, not in the sky. And it's really, really, really irritating. The Pluto-Neptune one is actually one of the earliest things that people worried about. In fact, it led to, I was just talking to some of the kids downstairs about this earlier today, it led to people thinking that maybe Pluto had actually once been a moon of Neptune and had gotten ejected but what we actually now know, knowing the orbits better, we actually know that they're locked together in this intricate dance where they never get close to each other. Neptune goes around the sun 3 times for every time that Pluto goes around precisely 2 times. And they're in this, it's a beautiful little dance. They're like this, so they never get close to each other. Pluto actually gets closer to Uranus than it ever does to Neptune. It's an astounding thing. 2 more questions. Okay, I'll have to do just one on each side.
What of the fate of the once postulated Planet X?
Yeah, so Planet X was sort of the thing that I started the story with. There's this large object out past Neptune that's causing these problems. Well, we now know that all of those early thoughts that Neptune was moving in its orbit a little bit funny were just incorrect observations. So that part we knew wasn't true. When I started this survey 7 years ago, we still thought there was a good chance that we might find something large out there that hadn't been seen in a sort of circular orbit like you would think Planet X would have. It's not impossible to hide these things. You'd have to put them much further out now than where anyone would think. But I think that the answer is that there's nothing out there anymore. We now know so much more about these objects that are on these very crazy looping orbits that if there were something large out there, they would be interacting and we would know. And so I think that's it. I think that of the major planets that we're ever going to have in the sun, they're going to be these 8 are going to be the main ones in circular orbits, and everything else outside that we find, even if they're big, they're going to be in these long looping orbits, not really like what we would call a planet.
When you find more information, are you going to be back around here?
If I'm invited back, I'd be happy to tell you more. Particularly if I find that Mercury-sized one out there, I'd be happy to come tell you more.
Thank you.